So next I want to go over strongly connected components, which is a concept of connectivity for directed graphs. Yeah, for directed graphs. So let's jump right in. So given a directed graph G, U is strongly connected to V if U can reach V and V can reach U. Okay, so whereas in undirected graphs, strong connectivity was a given, right? If you could reach, if you could reach V, then V could always reach you. In directed graphs, that's not a given. So, because connectivity is not a given in directed graphs, we introduce this concept of strong connectivity, which is two vertices are strongly connected if if vertex A can reach vertex V and vertex V can reach vertex A. Okay. So we need to define a relationship C where UCV if UCV if U is strongly connected to V. Okay? So this strongly so C, this strongly connected component relation, this strongly connected relation is an equivalence relation. It is reflexive, symmetric, and transitive, as we said before. So in the undirected case, this was true, and in the directed case, this is true as long as the two nodes are strongly connected. So the reason we're discussing this is because the strongly connected components partition the vertices of G. Okay? They break G up into several parts of strongly connected components. So we define this new notation SCC of U, which is the strongly connected components that contains the vertex U. It contains other vertices, and in fact, if the strongly connected, you could the same strongly connected component could be written as SCCV, SCC, and SCCU if U and V are both part of the same strongly connected component. They represent the same thing. So, for instance, in this graph, we have several strongly connected components. In the graph here, we have a strongly connected component that includes BEF. That is because B is reachable, it can reach E, and E can reach B. Similarly, E can reach B using this, and also B could reach E, and F could reach B, and B could reach F. So all these components, all these vertices together are strongly connected. Okay, and we have another strongly connected component here, and we have another strongly connected component. This one is important because we note that strongly connected components can contain only one vertex, as seen in this graph that has two strongly connected components that each have one vertex. Okay, so some problems for strongly connected components. Given a graph G in nodes U and V, can U reach V? How do we determine that? Given a graph G and a component U, can we compute the reach of U? Given a graph G and a vertex U, can we compute all the vertices that can reach U? That means that all the vertices where U is a part of their reach. So it's the reverse, right? These two are the reverse. This one you want all the nodes that U can reach. This one you want all the nodes that can reach U. And then, can we find the strongly connected component containing U? And then, can we find, is G strongly connected? I.e., does it contain a single strongly connected component? Does it consist of a single strongly connected component? And finally, can we compute all the strongly connected components? Those are the questions that we wish to answer in this lecture. Namely, those are the algorithms. Those are the algorithms we wish to develop in this lecture. Okay? And a lot of these can be solved by very basic algorithms, and a lot of them need more advanced algorithms. Okay, and yeah, and then we'll come back to this, and then we'll discuss that. We'll discuss solving these three problems using basic search next. Thanks.